Okay, hello everyone. My name is Krishna Naidoo. I'm a postdoc at the Institute of Cosmology and Gravitation at the University of Portsmouth, and today I'm going to be discussing how the preference for evolving dark energy measured by DESI may in fact be evidence for modified gravity. So I want to start with some context. So since the discovery of dark energy almost 30 years ago, our understanding of cosmology as a whole has been dominated by the standard model of cosmology, lambda CDM, where dark energy simply is a cosmological constant, which we call lambda. So lambda is just a constant repulsive force that fills all the space and appears naturally in Einstein field equations for general relativity. It's been incredibly successful in explaining almost all observations we've seen, and also making predictions for a growth of structure and the nonlinear distribution of matter that we see in simulations and in observations. But it looks like lambda's dominance is showing cracks or weaknesses, and in a more serious way than we've seen before. Because we've had tensions in cosmology before, but usually those measurements involve complicated modeling or astrophysics, so much so that it's not been very clear whether there was something wrong with lambda CDM or if there were problems with the observations. But this tension comes from a really clean measurement, BAO. So what's kind of brought this on? And its measurements of baryonic acoustic oscillations measured by the Dark Energy Spectroscopic Instrument. BAO are frozen sound waves caused by a tussle between gravity and radiation pressure in the baryon photon plasma during the early universe. This leaves a characteristic feature in the distribution of matter, which looks like a bump in the two-point correlation function. And you can think of this as a set of rings that are preserved in the matter distribution. And we can use this as a standard ruler because this feature is frozen in and will appear at the same scale at all times. And this is what DESI has measured. So DESI found that when you combine CMB and DESI BAO and supernova, there was a preference for dynamical dark energy. And dynamical dark energy refers to models of dark energy where the equation state changes over time. This is a completely phenomenological model. So on this plot, the x-axis refers to the equation state now, and the y-axis refers to the gradient of that equation state. So this spot here, where these contours should lie if the underlying model is lambda CDM, is marked on the graph. So if you can see, the data prefers a non-zero gradient and also a non-1 constant. Okay, so what does this mean for dark energy's equation states? So what it implies is dark energy is phantom in the past. It crosses a phantom divide at redshift 0.5 and then becomes non-phantom. But the constraint on the equation state at high redshift, I think, should be taken with a bit of a pinch of salt, because this actually shows you the limitation of this parameterization. So if you actually do the same measurement but binned in different redshift slices, you actually see that the high redshift measurements are still consistent with -1. So I think the key thing here is that what we are seeing from data is that we have a preference for dark energy that is phantom around redshift 1, crosses the phantom divide and becomes non-phantom, while at high redshift it's a little bit more unclear about what's exactly happening with the equation state, because it's still consistent with -1 and the errors are very large. Now here's the problem. So unlike lambda CDM, where we could point to Einstein field equations to justify lambda, we can't do this here because dynamical dark energy is purely phenomenological. So it doesn't tell you what dark energy really is, and it gets worse than that. If we take the simplest explanation that this is simply a scalar field, then observations want us to do something which creates instability. So I think the best way to look at this is that this is not the ultimate theory, but instead a kind of stopgap useful model that will guide us to the true theory, assuming that the behavior we're seeing is is the true behaviour of dark energy. So with that in mind, let's talk about Horndeski gravity. So Horndeski gravity is the most general way to describe a theory with a scalar field that is coupled to the metric, and it's written in such a way that it has nice stable properties. The model is defined by two new functions, phi, which tells us the value of a scalar field, and x, which tells us the time derivative of this field. The dynamics of the model defined by four free functions of phi and x. The first k function describes the kinetic energy of a field. The g3 function describes something we call braiding, which you can think of as friction between the scalar field and the metric. The third g4 is the gravitational coupling, which you can think as a time-varying Newtonian gravitational constant. And g5, I'm going to ignore, because the very big multi-messenger event GW170817 basically showed that gravitational waves move at the speed of light, and if G5 was actually active, then this wouldn't be true. So it's fairly safe to say that G5 is either really small or it's zero, and in this work we assume it's zero. So this model was invented by Gregory Horndeski, who wrote his paper on this model in 1974. It was mostly ignored. He decided to leave academia and become a painter, and this is some of his lovely work. And I've included some of these paintings in my talk today. So this Horndeski work was then picked up by cosmologists in the 2010s when they realized they could describe many different modified gravity models in this kind of unified framework, including models like the cubic Galilean, F of R, DGP, camouflage, and many more. Alright, so to do this analysis, I'm using HiCola, which is a piece of code designed to compute the background of the universe and to compute approximate n-body simulations in Horndeski space. So HiCola was originally developed by Tessa Baker, Bill Wright, and Ashim Gupta, but I've been working with Tessa Baker to basically rewrite the code to make it more user-friendly, more stable, and I've added a whole bunch of new functionalities that make HiCola really powerful for exploring Horndeski model space. So how does HiCola work? It's split into two parts, the front end and the back end. The front end is a Python-only piece of code where a user defines the three functions k, g3, and g4. We then construct the model symbolically, a bit like Mathematica, but in Python, and we numerically solve a bunch of coupled ODEs to solve the background quantities. So we're essentially working out how a scalar field is evolving, what's happening to expansion rate, and also computing a whole bunch of other functions, such as the growth function, screening effects, and many more. In the backend, we feed in these quantities into a Cola solver written in C++, which gives us approximate n-body simulations. The work I'm going to discuss is going to focus on the front end and model exploration. So one of the simplest Horndeski models we can consider is something called the cubic Galilean model. This is a model which is only dependent on the scalar field's derivative x and only has one free parameter. So although you can see two free constants k1 and g31, these two constants are actually defined by one parameter. But if you remember from earlier, DESI BAO is showing us that dark energy is behaving phantom-like at late redshifts before crossing the phantom divide at redshift 0.5. But cubic Galilean is always phantom, and it doesn't matter how you vary the single parameter that it has. It's just a generic property of these types of models, and this is actually true for all models that are only dependent on x. So we decided to look at models that are close to the cubic Galilean because this phantom behavior is actually very good early on. So, at late redshift, having this phantom behavior is a good thing. The thing we want to we want to solve is, can we cross the phantom divide here? And it turns out there's a whole family of models that can do this. So in these models, we add an extra phi-dependent function to the k and g3 functions called squiggly k and squiggly g. But for this to work, the k function must decay as long as it doesn't go below 0, or the g function must grow. So at early times, since phi is small, we can write these equations such that at early times both of these functions become 1, and in this way the model follows along the cubic Galilean model, but only deviates at late times. Oops, sorry. And for this reason, we call these models asymptotic cubic Galilean models. So if we take these two models and constrain them with DESI BAO, DES supernova, and a compressed form of a CMB likelihood, we get the exact phantom crossing behavior we were looking for. So we found two models of Horndeski gravity that can reproduce the dynamical dark energy behavior favored by data. The way this differs from W0WA is that at very late redshift, very large redshift, we see that this tends towards -1, which is not the case for W0WA. But there is a catch to these models, and it's that some of this parameter space will give you negative ISW cross correlations, which, without going into the details of the ISW, it's an effect caused by CMB photons gaining and losing energy as they traverse large-scale structure. It's a very weak signal, but almost all observations find these cross correlations to be positive. So if we now add in this extra constraint that the ISW needs to be positive, then this makes the equation state much shallower than what we were seeing before. And you might be thinking, okay, so we're constraining this and we're making the equation state even shallower. Does this actually fit the data very well? So here is what the raw behaviour measurements from DESI look like in comparison to lambda CDM. So the dashed horizontal black line is lambda CDM following constraints from Planck only. The grey contours are W0WA from constraints from DESI, BAO, lambda CDM, and DES supernova. So if we place in these Horndeski models, and we see it's a perfect fit to the data, and very much follows the kind of W0WA behavior. And this remains the case even when we constrain the models to have positive ISW. So in terms of model comparison, how do these models compare to W0WA? In terms of an improvement in the chi-squared, W0WA gives you an improvement of about -13, while these models give you an improvement of about -10 or -11. So not behaving as well as W0WA, but they're in the same ballpark and all doing much better than lambda CDM. If we look at the Bayesian evidence, here we kind of see a reverse picture where these models are favored instead of W0WA, but very slightly. They're generally all behaving around, or giving you a value around 2, which you can think of as a kind of moderate preference for these models. For a preference to be significant, we would need a Bayesian evidence of around 4. So in both of these comparisons, we are seeing that we're definitely preferring these models over lambda CDM, and they're behaving at the kind of same sort of level. The difference here is that W0WA is a completely phenomenological model, while these models are grounded in a kind of better theory. We have a better understanding of what's happening with dark energy, or how dark energy is being produced, per se. Okay, so if dynamical dark energy is really evidence for this type of modified gravity, then we should expect to see lower ISW. So the low L modes of C and B should be lower than what you expect from lambda CDM. There is some tentative evidence for this. But the other thing that we should see is more lensing, which has the effect of smoothing these curves. Again, there has been tentative evidence and signs of this in Planck data. In terms of a growth of structure, there are two potentials we need to be concerned about. The gravitational potential given by the Poisson equation. This is a potential that is influenced by matter. And then there is the veil potential, which is a potential experienced by light. In GR, we tend not to discuss or distinguish between the two because psi and phi are the same. But in modified gravity, you have these. You can quantify the difference between these models with an extra term called mu and sigma. In this particular model, mu and sigma are the same, but they are both greater than -1, which means we should expect to see more growth and more lensing. But if we look at the F sigma 8 predictions for these models, we see that the growth of structure, there's not a huge shift. So even though we expect to see a shift, it's not a significant one where we would expect this to be ruled out by constraints from growth. Okay, to summarize, I think we're in a very exciting stage in cosmology. Lambda is finally showing cracks. Although dynamical dark energy is preferred by current data, the model doesn't actually tell us what dark energy really is. We've shown that this behavior can be reproduced by a whole family of Horndeski gravity models. The predictions from the model appears to be reasonable, and now we need to rigorously test the model against all cosmology has to offer. So the next step is to test this at the linear level, which means testing against a full Planck likelihood, two-point clustering, lensing, and other measurements. So we will also be looking to run simulations of these models, which we're in a very privileged position to be able to do because we're working with high Kohler. So that's something we can directly test with observations in the near future. So thank you for listening. This talk is based on a paper which we are currently writing, but that should appear in the archive by the end of this month. I'm looking forward to discussing our work with you and speaking to you more at the conference. Thank you.